Hi, my name is Jatan Buch, and I'm a graduate student at Brown. And I'm going to talk about dark matter substructure under the electron scattering lamppost. This is a paper that appeared last month with collaborators here listed at the bottom of the screen. And I'm excited to share our results with the participants at Cosmology from home. Diving right in, here's the outline of my talk. And I intend to spend quite a bit of time in the introduction, motivating why a primarily cosmology audience should care about the Gaia era, but also what we can do with dark matter detection experiments that rely on electron recoil. And then I'll conclude with forecasts for next generation experiments, and then pose like an interesting question about not just what we can do with new astrophysics at these terrestrial experiments, but what we can use these terrestrial experiments to sort of probe some questions about the astrophysics. Okay, so the introduction is simple. This is the principle of direct detection. You just wait and see if a dark matter particle from some astrophysical distribution comes and scatters a standard model particle and produces like a visible signal in form of a photon or an excitation. And this is a very successful experimental program, which is, this is a plot that most of you should be familiar with, where you have the cross section versus mass, the mass being in GeV, and the cross section being in centimeters square, where the program has been, as I said, very successful, and we've almost reached the neutrino floor at heavy dark matter masses, but that is not the focus of this talk. This talk is going to focus on the lower mass region, where people chiefly probe with dark matter electron scattering. And even though I'm going to talk only with semiconductors, there's been some exciting work here with atomic targets as well, namely the S2 only analysis, where people have looked for Migdal scattering and just dark matter electron recoils. And so the lower mass region would be the focus of my talk, especially with semiconductors. So the motivation is twofold. One is, as I mentioned, what are the prospects of detecting a dark matter signal with the next generation electron recoil experiment for a given dark matter velocity distribution? But then there's also the next logical question, where you assume discovery and you ask, can you distinguish the effects of different substructure in a statistically significant way? And also a warning that this is unrelated to the recent electron recoil excess reported by Xenon 1 ton. This is the S2 analysis that people talk about. And in this case, the recoil energies are order keV, while we focus on an order about 10 eV, because that's typically the band gap energy or the binding energy for heavy atoms like xenon. Right. So moving on to what the substructure that has been discovered in the Gaia era. But before I do that, I want to spend at least one slide advertising what a beautiful mission Gaia is. There's incredible physics that has been done already, and a lot more that'll be done by the end of its mission, where it'll have positions, parallaxes, and proper motions for about 1 billion stars, which is still about only a 1% of the Milky Way, and it'll have a petabyte of completed data set by its end. What Gaia provides for our purposes is astrometry, photometry, and spectrometry, and you can combine this with existing catalogs like SDSS to identify these kinematic features called debris flow, the most famous of which is the Gaia sausage, and streams. These streams here, where the name of the game is simple, where you have a subhalo, which is usually a dwarf galaxy. It dumps its stars and dark matter as it's tidally stripped while falling into the Milky Way. And the idea is that if you look at certain kinds of stars, these can be, in principle, good tracers of the velocity of dark matter. And I'll talk about that in a second, and you sort of also verify this with numerical simulation. The next generation, so to speak, or beyond SHM, is all about using data to empirically model the dark matter velocity distribution, and this is what we're going to use to see if there's any interesting things that happen with direct detection experiments. I also thought it would be useful to show a simulation, although I should say that I'm not a simulations person, so this is due to these two people here. And so what I'm showing is a small galaxy being tidally stripped into a large galaxy. So this is basically what happened to create the sausage or the streams. And you can see that it's not just randomly being stripped, all these stars. There's some coherent motions here, and it's leaving behind some substructure. And this is essentially what these groups did right here with the new Gaia data. They also looked at in particular they looked at the metallicity and velocity space, and they identified this population which was previously unknown, and this is what they dubbed the sausage. And this is they did follow up numerical simulations, and they found out that if you basically have similar properties as you observed in the data, and you have similar merger history and so on in your simulated Milky Way galaxy, the dark matter and the stars will have similar velocity distribution. So if you pick the right stellar population, you'll get the dark matter distribution. The only unknown, of course, being the dark matter fraction, and there's clever ways to obtain that. But the other substructure here are streams, and streams are typically at the outset expected to be a smaller substructure fraction as compared to the sausage. So sausage is supposed to be about 40% of the local dark matter, whereas streams are only expected to be 10 to 20%. And the qualitative difference is that streams were formed by recent mergers, whereas the sausage was formed by a relatively old merger. And as I said, that these are the streams that I'll be focusing on. And again, there's broadly two kinds: the prograde and the retrograde. The prograde being streams that moves with the sun as it rotates the galactic center, and the retrograde means that it's moving against the sun. The caveat with streams is that there is no star dark matter correlation. But if the progenitor was a dwarf spheroidal, maybe some simulations show that there is a better correlation. But it is still like an open question. There's much research going on, but for our analysis, we'll just assume that there is perfect correlation. Now this is a useful way of thinking about, wait, okay, fine, these are astrophysical phenomena, but how does my dark matter detector see this? And this is chiefly through the velocity distribution. This is the total velocity distribution. It's the profile as a function of the velocity, and this is something we call GV min, which is nothing but the inverse moment of this velocity distribution, integrated from a minimum velocity determined by kinematic constraints of the detector, and an escape velocity, which is just the velocity, the maximum velocity a dark matter particle can have without escaping the gravitational field of the Milky Way. We look at three substructures here, namely NIX, SHM, and S1. And we also introduce this parameter VMP, which is the most probable velocity. And a heuristic way to think about this is that the inverse of the VMP gives you the height of this plateau, which means that if you have a higher VMP, which S1 does, you have a lower plateau, but it stretches up to a very high V min, or rather it goes up to very high V min, whereas for NIX, you have a lower VMP, but you have a higher plateau. And this will show up in like the behavior of the constraints or the discovery reach contours that we'll plot. The other characteristic feature of streams or substructure in general is annual modulation. And here, with the example of two streams, TOI1 and TOI2, you can really see that it's not just the sun moving around the galactic center, but the Earth moving around the sun. which also creates a relative velocity difference between the dark matter and the Earth. And this shows up in something that we call angular modulation, because of course the Earth has a period, or the motion period of about a year. And you can see this as the difference between GV min minus the average GV min as a function of time and V min. Okay, so what happens in dark matter detection with electron recall experiments? Well, the name of the game is the same. You have a dark matter that comes in, excites an electron in the valence band, and you know, makes it jump across the band gap and go to the conduction band. The important thing to note here is that there's a recall momentum that is determined by the electron velocity in the band, and the energy transfer should be greater than this band gap energy E gap, which is usually order EV. And so you can see this cartoon: dark matter comes, excites the electron, and then goes away. And this rate of exciting the electron from the valence to the conduction band is given by the usual n sigma v formula, where n is just rho chi by m chi, sigma is determined by the particle physics, and this GV min is the average, is this integral as we discussed. The difference from nuclear recoil is this response function, because the electron is no longer free, or like the atom in nucleon case, but in this case the electron is no longer free, and you need to account for this, the band gap, the band structure of silicon or your semiconductor. And then this exercise was first carried out by this group, and you can see here, you know, I show this form factor as a function of the recall momenta and the energy. And also shown here are these contours for V min equals VMP for NICs, SHM, and S1. You can see that for lower Q and high E, you have the maxima of this form factor, but you're kinematically limited depending on your substructure. So this creates this other effect where it's not just your GV min that determines your the shape and the normalization of your recall spectra, but also this interaction between the response function and the GV min. And this is most clear in this plot, where you can see that as I increase the mass, so if I go to lighter contours, for different substructure, for NICs, SHM, and S1, these have different dependence when I sort of convolve them in some sense with the form factor. And this, you know, for the simple case of 20 MeV and then some cross-section value, you can see this for like 100% NIC stream or 100% S1 stream, where this plot shows in these colors, the band, it shows the peak and the trough of the modulation. So these are the delta events, and then, you know, the numbers here show the absolute number of events. But you can see qualitatively that for higher masses, you go to progressively higher energies, which in this case comes to higher Q, and not just for higher masses, but also for higher for substructures with higher VMPs, which in this case is S1 relative to, say, NICs. So you see, like here the peak is mostly in Q equals 1, whereas here it's between Q equals 3 and 4. And so this is really what the experimental spectra that you see, that a experiment sees really, and the idea is like, can we say something meaningful about this, you know, in terms of the constraints that we set. So we use forecasts for next generation electron recall experiments to hit the point home. And like I said, you know, the method that we should use, or we do use, should incorporate both the time and the energy spectra, and this should, you know, this incorporates all the phase and the VMP information. So here, what I'm showing are the 5 sigma discovery reaches, which is essentially asking the question, what is the cross section and the mass necessary to see a 5 sigma detection of dark matter. There's 3 contours here that are for the exposure of 1 kilogram year with the next generation. In this case, just a sensei-like experiment, but it could be your favorite electron recall experiment. And we've used different background configurations here. So this is max, this is optimal, and this is the mod, which is just the annual modulation. So the subtlety here is, of course, that if you use annual modulation, you know that your background doesn't modulate. So this is a background free channel, but you pay the price that you're looking for modulation, so which is a smaller signal than just the average, which is for max and optimal. And these are essentially 2 background models. And you can see that for some part of the parameter space, the modulation is just a cleaner channel, and you'll be able to, especially for low dark matter masses, be more sensitive. We also show the results for a light mediator. So here, the idea is that it's a contact interaction. But what if you have a model where you have a dark photon mediator, which is massless? So you have a 1 over q squared, like a Rutherford-like scattering, in which case your spectra is squeezed to lower Q bins, capital Q bins, and you are in some sense more sensitive because you can go to lower cross sections. Also indicated on these plots are the current constraints from Sensei, Xenon 10, and Xenon 1 ton. Okay, what happens with substructure? Well, with substructure, the behavior is, so we only show what happens with modulation because it's a quote unquote clean channel. And you can see that, if you assume 100% of dark matter to be in NICS or in S1 or in any of these other substructures, the constraints significantly vary from SHM. And all of this can be explained with the features in the velocity spectra or in the GeV min spectra that we were talking about. Like, for example, in case of S1, you see that it is more sensitive at low dark matter masses because you see the V min has an inverse MCHI dependence, and that means that you go to high V mins to get a recoil event, but the only sort of contribution there in terms of substructure is from S1 as compared to, say, SHM or NICS or any of these other substructures. So you see you have a much stronger discovery reach. Whereas there's some other features that you can identify, namely with the dispersion and the coplanarity, but I won't go into that. The only thing that should strike you is that if you have 20% or NICS or S1 with the other being SHM, which you would assume to be the realistic case, you'd be inclined to say that there is nothing, that I shouldn't bother too much about it. There's not too much going on, and maybe these experiments, while interesting in the science sense, may not be able to tell us too much about the nature of the astrophysics. But that's not quite true, as we show. If you look at the prospects for astroparticle physics, which is sort of flipping the direction and asking what can direct detection tell you about astrophysics, well, you get some interesting results. So I should say, at the outset, that here we assume that you've discovered dark matter. The cross section is chosen so that you assume like a phi sigma discovery, and then you show that for different benchmark masses and cross sections for S1 and NICS. And again, for our 2 models, max and optimal, you show these 1 sigma degeneracy contours, which essentially show how well you can resolve the substructure fraction in each of these 2 cases. And if you have an optimal background model for a 1 kilogram year exposure, you can really do quite well. With the maximum background, not so much. And again, these behaviors can be very easily explained in terms of the velocity parameters, and you should look at the paper for more details. The main takeaway point, of course, being that okay, so this is the other example where you have two substructures simultaneously along with SHM making the rest. So if, for example, if you have 10% S1, 10% NICs, the other 80% will be from SHM. But the idea is, can I sort of distinguish between these two, which was one of the motivations. And the answer is yes. Of course, this assumes that I know the astrophysics, the velocity distribution quite well. But in principle, this shows that it can be done. The other thing to notice here is that if your VMPs are similar, so NICs, S2A, and SHM are fairly similar, there's huge degeneracies. But if you have different VMPs, well, you can start resolving some of the degeneracies. Lastly, I'll just say that this is using the Swordfish sort of code that was developed by Edwards and Vinegar, and it's just a very fast way to make these benchmark-free degeneracy contours. But again, the takeaway in this case should be that, well, we can use direct detection experiments, in particular electron recall experiments of the future, to say something about the astrophysics. And with that, I conclude. Yeah, thanks so much for your attention, and I look forward to the question hour and great discussion. Thank you.